Okay, then we start up. So it's in quite an okay room, actually, I would say. We are going to be here on Thursdays, except week 8 and 12. Now I don't recall what exact dates they are, but still some time. 8, maybe that's next week already. I'll translate it into correct day numbers. So, but as you see, most of the time we will be here on Thursdays. You had been given some material and also the demos. I'll try to put them out here. I've forgotten to give you the diffusion equation and also the advection. I'll put them out. You'll get them. So that's the demonstrations that we ran yesterday. So we have been through quite a lot, actually. This through-hole example and the max-mean method also. So I will start by peeking into actually using the max-mean method for the entire Navier-Stokes. So here I've stolen it from a couple of guys. You have the same material, written maybe a little bit better. Here I think, no, not that one. It's not here. Well, I think you have it here somewhere. In this compendium, first part. Looking into the stability, chapter 2.7, where actually the entire Navier-Stokes is then suffering from this max-mean method. Here we go. So the entire method is actually described here. All you need to ensure that your new value is bounded between a maximum and a minimum value. Very easy. If the sum of these coefficients is 1, then you can use the method. And then you know if all these coefficients are positive, then you are dead certain that this will be stable. Then x will be bounded. Very crude method, but frequently all you need to know. Very easy to use. So definitely something you should be aware. Here I now use the method on the entire Navier-Stokes. Actually, I think here the Struhel number has been defined wrongly. Normally you have it as just the Struhel number, not 1 over Struhel number for the time derivative term. Not that it matters. The Struhel number is just a time scale anyway, so he's going to drop out either way. The trick I've done here to be able to do this is saying that this equation, that's for an arbitrary velocity w, and then I don't specify it, which one that one is. Of course, in a two-dimensional case, it's either u or v. And if you choose either u or v, you are in trouble, because then you have these nonlinear terms here. Then you have functions multiplied with the derivative of functions, hence any analysis is impossible. So we have to linearize. So the way I treat them as two different velocities. Either, even though I know sometimes they're going to be the same, but I sort of treat them differently anyway. Here, the function f then includes pressure gradient, gravity, other forces if you have some. So then use the max mean method on the FTCS scheme for this one. And the FTCS scheme, straightforward, as we have it in the Sola algorithm as well. Double derivatives with respect to x and y, convective terms, also central space differencing, and then the time derivative, forward time. So yes, you have an explicit first order Euler scheme in time. Very easy to solve this one. So the stability problem that we can include here, that will then be sort of not the entire projection method. Remember there you also have the trouble with the pressure, you had a Poisson equation for the new pressure, and then update the velocities. That's not covered here at all. This is just sort of the first part, just updating the velocities actually. But we can learn a little bit at least from the stability analysis from this equation alone. So here a little algebra to write it on the form the new unknown velocity. Actually it should be an n plus 1, of course, not just n, equals, and then the 5 old, say, neighbors. You have the center point and the 4 around it to create the derivatives and double derivatives. The square brackets, they are now just coefficients. Although you see the coefficients also include the local velocities, small u and small v. But never mind that, treat them as constants if you like. So, and if you add all these squares together, you get 1. Very nice. So, rewriting them now and demanding all these coefficients must be positive, we get these criteria, which then are a little bit strange. The last one we sort of can understand. That includes a delta t. The two first ones, they don't include delta t at all. So where do they come from? They are actually a demand for spatial resolution. Depending on the Reynolds number, you have to have so and so small delta x and delta y. You have to resolve the physics in the problem. Here, I'm not interested in spatial resolution. I'm interested in stability criteria, so I cheat. I use the CFL condition, Courant-Friedrich-Levy condition, to rewrite the delta x and delta y here so that I can use delta t instead. Just saying that the CFL condition then is 1, then I can rewrite these spatial demands for resolution to something as a demand for the time step. So that's one way around it. We'll have a little bit more peek into that one today, not with the entire Navier-Stokes, but we will get the same criteria as well. So to sum up, all the criteria that we have then in the Sola algorithm. First one, that is the CFL condition, Courant-Friedrich-Levy condition. You can't look at more than one cell during one single time step. Hence, the delta t has to be so small locally, multiplied with the local velocity, that you don't go further than 1 delta x or 1 delta y then in the delta 1 delta y, yes, in the y direction. Because the discretization scheme doesn't take the next cells into account. And the next demand, we have actually seen this one already, but not in a two-dimensional form. So here we will have it a little bit more complex. I think we had something like h over 2 times the viscosity. That was what we found when we looked at the one-dimensional diffusion equation. So again, then the demand here says we are only taking the neighbor cells into account. Then if you're going to have some diffusion effects from the next cell, okay, then it doesn't cover it. So that demand a small delta t here. So the last one, a little bit more tricky to find. This one evolved from the max-min method on the entire Navier-Stokes. And this one is hard to find other ways. What it actually physically do is to ensure that the total diffusion coefficients in your numerical scheme is positive. We will also address this one a little bit further today. So, of course, this is boring math, a lot of algebra to get the expressions, but yes, it's possible actually. And yes, you can learn a little bit from it. Yep.
Didn't you say that the stability methods were only valid for hyperbolic and parabolic?
Yeah, the stability issue is only for parabolic and hyperbolic. That's true. The momentum equation is in general hyperbolic, parabolic, and elliptic. All three at the same time, if it's incompressible flow. So then you have to take sort of all the three nature into account here. You might make it easier for yourself if you think the Navier-Stokes is elliptic in space. Remember, we got the Poisson equation for the pressure. That was solving the pressure field at this time level only. So elliptic in space. That demands then that we have to specify boundary conditions all around because it's elliptic in nature. So in the space, you need boundary conditions around the entire domain. Then in time, then it's a question, is it parabolic or hyperbolic? There you could sort of choose, is it compressible, incompressible? And there you then need initial conditions, of course, to get things started, and you need boundary conditions for all times, or else you can't get a solution. But in the future, you don't have to know anything. You can march the solution forward in time. So they're parabolic or hyperbolic nature. Okay? Other questions? So whether you want to look at this one or the other one, they're sort of the same. Your choice. Yeah, I have the same remarks here as well from the Sola algorithm, just handwritten. And here we then have an interesting thing, which we are also going to have a look into. Yes, you can sort of rewrite it back again to get the same demand that we had from this max-min method on the entire Navier-Stokes. Something demand for the delta x has to be smaller than something. Why is that? So yes, it's true. Although here it has to be smaller than 2 divided by the Courant number, or even bigger than 2 multiplied with the Courant number. So we will have a look into that one today. You can find it from a stability analysis on the steady, what's called a linear Berger equation. So that's what I call an advection diffusion equation, steady state. So you can find the same criteria from that one, which is also what we are going to do today. So this one we looked at yesterday. And then the advection equation, doing a straightforward stability analysis on that one, we got a surprise. It was unconditionally unstable. It explodes no matter what you do. And the remedy then we did first order upwind. So yes, that's possible, and if you do, you get something unconditionally stable, but at a price. We got a very diffusive effect, smearing out all gradients. So we have a diffusion mechanism into the scheme that wasn't there initially. And diffusion, what he does, takes a jump and then smear it out, dampen down any violent behavior. So yes, of course, this is a stable effect. And the different diffusion mechanisms that we can find, of course, you have the physical kinematic viscosity. You have maybe a turbulence model. And a turbulence model, we'll see that later, a turbulence model, he actually cheats. He introduces viscosity into the problem. So much viscosity that the motion is damped down and you are actually able to solving it. But of course you will have control over the added viscosity, turbulent viscosity. So the answer should still be correct, more or less at least. Then I differ between artificial and numerical. They are arising from your choice of numerical scheme. The numerical part there, it's unavoidable. It's going to be there, and we don't like it because he's negative. You'll see it. He's negative, and he tends to do the opposite then from doing things stable. He will, if he finds a gradient, he will increase it. So there we have a risk of exploding our numerical solution. So the numerical, he's there. Artificial, that's something we can choose. We create a numerical scheme that has some additional artificial fixtures viscosity into it, like the first order upwind scheme. If we choose that one, then we add viscosity, we know that. So then that might be at least more stable. You even have other diffusion mechanisms. We're going to see that later. So say for instance, you have your numerical mesh system, something like this, uniform rectangular cell systems. And you now add a flow 45 degrees on the grid lines. There you're in trouble. Not from any of these, but you will actually see just from interpolating, finding or calculating the velocity field here, you will have a smearing effect because the streamlines will then be at an angle on your computational mesh. That also induces or may induce a diffusion effect. You will smear out gradients in the directions where it's not supposed to. We will see examples of that one as well. So actually 5 then different diffusion mechanisms. And all in all, hopefully it should be positive. So when you write your Navier-Stokes, you have time derivative, you have the convective terms. Here we have some pressure gradient, and then we have a viscosity, and here comes first of all then the double derivative with no, we better write that one differently. Write it like this. Double derivative with respect to the different directions multiplied with, and then you have the first one, that was the viscous diffusion. Then you can have turbulent viscosity. Then we have the artificial, what should we call him? New artificial. And then we have the numerical. And finally, grid. So if the square bracket, some of them are positive, that should help to keep things stable. Or to say it in another way, if the square bracket is altogether negative, it's going to explode. So that will be one stability criteria we have to watch out for. As a test example, we have this model equation. It's a sort of a one-dimensional version of a Navier-Stokes. It's a Burger equation, and here even a transient Burger equation. We have made a linear version of it just to ensure that we are able to do some analysis. So instead of u dx, as it should be, I write a velocity a, constant velocity a, times du dx. Then we can use our techniques, finding the stability criteria here. We are going to make a lot of derivatives now, so I changed the notation. I use sub for derivatives, or else we are going to get tired by writing. So equation 1, this is my original. That's where we start, original partial differential equation. One-dimensional in space, and of course also in time. Here we now have an FTCS scheme, but not a pure central scheme. I have mixed it as a hybrid scheme. If you look at the term that involved a du dx, and now we say a is positive, so we know the information is traveling to the right. If you want that one to be a central space scheme, you would write him a over 2 times delta x, and then multiply with u, what have I used, j plus 1 minus u j minus 1. That's a central scheme. That's second order accurate. Order delta x square. The other choice, first order upwind scheme. Then we use a over 1 single delta x, and then we create the derivative by uj minus uj minus 1. This one is only first order accurate. That was sort of the choice. But here I've written it on the form with an alpha. So you see, if alpha equal to 0, the last parenthesis disappears, and we are left with a pure central scheme. Then we have this one. Alpha equals 1, then a little bit algebra, and you will be left with this version of the same term. So both are present. And now you can choose alpha equal 1/2, take 50% of each, sort of a hybrid scheme. That's quite possible. Or 25%, 75%, your choice. So possible there to mix up your scheme a little bit if you want to. This, of course, to see the effect afterwards. So what we are aiming for now is what's called a modified equation. And I want a modified equation. How to obtain a modified equation, or what is a modified equation? Well, we are not always agreeing what a modified equation is. I know Verziger, he defines it differently than I am going to do. Well, to obtain it, first you take everybody different from your center point. This is the center point. Everybody else you have to insert an entire Taylor series to represent them. So that's the first step. And here we are going to need a Taylor series in time, forward in time. We have n+1 when we do the first order derivative. And then I need both directions in space. So jn plus and -1. So I need those three different Taylor series to insert into my numerical scheme. So this is the first step to achieve a modified equation, to find a modified equation. Also, if you can recall, this is the first step that you do. This is the working procedure. If you want to find out, is my equation, my discrete equation, is it consistent? And what is the order of my scheme? Here I just stated that this is second order, this is first order. Well, to see this, you have to do this working procedure. I'll show you. Here, everything now is substituted into the discrete equation system. And yes, you get rid of a lot of things here. And now, to ensure that your equation system is consistent, what was the demand? Consistency. Well, you let all the deltas go to 0, delta t and delta x. Then your original partial differential equation better show up, or else you are solving the wrong equation. So that's quite essential. So if you rewrite it here, you'll see it better. So the top line, yes, it is indeed our original partial differential equation. And you see the other terms there, they are, everybody has a delta included in them. So yes, it is consistent. That we can conclude. Furthermore, from that expression now you can also see what's the accuracy of my numerical scheme. Well, the biggest outer terms will be of order delta t. I have also included delta t square, but I mean delta t is small, so delta t square is so small that you can forget him. It's of order delta t in time. And in space, well, that depends. If I choose alpha equal to 0, then I get rid of this term. Then this will be the biggest outer term in space. Then it is second order accurate. If I choose alpha equals 1 or anything different from 0, then this term is included, and that one is indeed first order accurate. And here Verziger stops. He claims this would be the modified equation. I don't agree with him. I want the modified equation differently than this one. I don't want any time derivatives to the right. Here we have a double derivative with respect to time. I don't want that one. I want only x derivatives here. So I have to get rid of him somehow. We rearrange the same equation, then we have this one. So I just write it on the form almost equal to 0, equal to hot, meaning higher order terms. And this I'm now going to reorganize a little bit. For starters now, I want to get rid of this double derivative with respect to time. The first one, that's okay. That's part of the original partial equation. So of course, that one I want to keep. But get rid of this guy. Remove him. How do we do that? Well, we use the same equation. If you take the time derivative of this entire equation and multiply it with minus delta t half, and then add these two equations together, then then he disappears. So that will be the first step here. Take the time derivative of the entire equation number 4, multiply with minus delta t half, And then you take the difference between the original and this one that we have changed a little bit. But of course, taking the time derivative of this entire equation, you will have from the first term, okay, then there you get the double derivative with respect to time. So that's okay. The next term, that's not so funny. Now I get this u, both time and space derivative. So that will be my next step, to get rid of him as well. And you have to do this as many times as necessary. So what we have to do here is to flip this one, if that's possible. No, it's not. Isn't it possible to flip him? No? Refresh, thank you, no. Well, let's do this differently. I can't use it differently. Okay. You are going to have your neck broken. Well, if you have it in front of you, you could see it. The idea goes as follows. You set up sort of a matrix, large table, and then here you write all possible combinations that you have. You have time derivative, you have space derivative, you have double time, you have time and space, you have double space. That was 2, and then you continue with 3. U 1, 2, 3 in time, t, t, x, and so on. And then our original equation, well, he then had the coefficient 1, time derivative. In front of the first derivative, we have the velocity a. We didn't have that one. Not that one. We have this one. There we had the viscosity. But now I had everything on one side, so it was minus the viscosity, wasn't it? Yes. Minus the viscosity. That would be the original differential equation, and then nothing else. With my discrete sort of on the modified equation, modified as much as I have inserted the Taylor series, we have something more here. Then we had this term that we didn't want. He had the coefficient delta t half. This one we didn't have, and so on. We had some additional here as well, didn't we? Yes. Here comes plus, no, it was minus, sorry, alpha a delta x half. Yeah. So we had a couple of other terms as well from equation 4. So now the idea is get rid of all unnecessary time derivatives. We keep this one, that's okay. Get rid of him. How to get rid of him? Well, you use the original equation. You multiply with minus delta t half and take the time derivative of the entire equation. Then this term, he will now become a double derivative with minus delta t half in front of him. So when you add these two together, he will disappear. That's beautiful. But this guy, with an a already, time derivative, he will become this guy. Now we have a delta t half in front of him, minus a delta t half. I didn't like that one. Not good. Let's see. This term we didn't have, and here I will now have a txx. He is far to the right, so I don't care about him. Step number 3. Now these two is okay. Get rid of him. Get rid of this term. I don't want him. Okay, then I take a coefficient reading a delta t half, and then I take x derivative of the entire equation, d dx. What do you get? Nothing here. This guy will be TTX, something here. That's okay. No, sorry. The first one. Definitely something that we get here. Of course, that was the whole point. So here you will have plus a delta t half. And then this guy, x derivative, he will be something here. And what will it be? It will then read a times this one. So here we'll have something a square delta t half. That comes in addition. And now actually we can stop. Add everything together. What do you get? You will have ut. You have a times ux, which is very nice. And then actually, well, we can keep it as it is. That's okay. No. Throw everything else on the other side directly. We can do that. Because what's interesting now is the double derivative. Ux. What do we have in front of him? Well, we have the viscosity, now positive, because he's on the other side. I have this guy, becomes positive on the other side, plus alpha a delta x2. And then I have something here as well, negative, minus a square delta t half. And then higher order terms as well. There you have what I will call the modified equation. Let's see if I got it right. Yeah, looks okay. So we have three diffusion terms here, diffusion mechanisms. Kinematic viscosity, of course. Then we have a negative part. That's what I call the numerical part. He's negative. We don't want him. He turns up because I chose the first order forward Euler step. So sadly, negative. And if this guy becomes bigger than the viscosity, then everything is going to blow up. And you see, worst case scenario, you don't have viscosity. We are calculating sort of Euler code here, Euler problem, no friction at all. And then you see the linear Berger equation. He falls back to be the linear advection equation, which was unconditionally unstable. And here you see the reason. No viscosity, central scheme only. The viscosity, total viscosity, is negative due to this numerical viscosity. That's why he blew up. Okay, then we have a remedy possibility here. We choose an upwind scheme. We set alpha equals 1. Then this term comes alive. Then we have a possibility actually to find a solution. Yes, we have. And I think I've written it here. So that will be the demand, stability criteria. If you're using central scheme, you only have the viscosity and this numerical negative term. Delta t then has to be smaller than 2 times viscosity over a square, which is then one of the stability criteria in the Sola algorithm. Yes, it is. So this upstream discretization, when we use this alpha, well, with 0 kinematic viscosity, we have to do something. Then really we have no choice here. We have to use a first order upwind scheme. And also you see this alpha then has actually to be bigger than what's then the CFL number, the Courant number. Velocity times delta t over delta x. So bigger or equal should it be. Now we can say, look at the local Reynolds number. That's frequently something that people likes to do. Local Reynolds number is the length scale of delta x. So you can reformulate this square bracket, and then you can see here what you are actually doing if you are choosing a first order upwind scheme. If the cell Reynolds number becomes bigger than 2, well, say if it's equal to 2, then you have doubled the viscosity. That's what you physically are doing. So that means you believe you are simulating water, flow of water, and then you choose first order upwind scheme, then actually you have doubled the viscosity. It's not water anymore, it's a totally different fluid. So that's not nice. And if you have a high, very high cell Reynolds number, and they can be pretty high in a real simulation, 1,000, 10,000, then you see you are calculating a totally different fluid than the one you really wanted to. So upwind schemes, they are pretty nasty. What would be nice is if we could get the sum of these two terms to be exactly 0. Then we are talking. And people have been trying to get this correctly. You can remove 1a and the half there as well, of course. So then you are aiming for something like, what will it be? Alpha times delta x should be identical to a delta t. So that simply reads now, we should have alpha identical to 1, because a delta x, delta t over delta x, that's the same as the Courant number. And the Courant-Friedrich-Levy condition said that one should be equal to 1. So alpha should be equal to, well, actually your choice then of delta t. That's one way to deal with it. And yes, here it's possible. We have a one-dimensional problem and it's linear. Then you can play around with stuff like that. For a real problem, well, this analysis is not true anymore. We can't really do it. Second, if you have more than one dimension, this is not correct anymore. So in practice, no, you can't hope for letting these two terms kill each other. One positive, one negative, both of them actually an error. So we would like this one alone, of course, but in practice you can't really do it so easily. Okay, any questions so far? Then we take a break, and it's going to be a little long